All right, when we compute a definite integral using the fundamental theorem of calculus, our assumptions for the function are that the function is continuous on a closed interval, and that closed interval obviously is finite. And the fact that the function is continuous means it has no infinite discontinuities. So once we have those conditions met, and we have a function that has an elementary antiderivative, then we can use the first fundamental theorem of calculus to evaluate the definite integral. Now what I'm going to do in this video is begin to extend that concept to integrals that either have an infinite discontinuity, either at one of the endpoints of integration or somewhere between, and for functions that have that we want to integrate over an interval that is not finite. So we're going to start with what are called type 1 improper integrals. All right, so an improper integral is any one of the types that I just described. So a type 1, so let's start this here. Type 1 is one where the interval over which we're going to integrate is infinite. All right, so we want either the antiderivative from a to infinity of f of x dx, or negative infinity to b of f of x dx. All right, so we'll tackle those two types in this video. And let's take a look at an example. And so I'm going to use as my first example the function y equals 1 over x squared. And so if I have y equals 1 over x squared, and I take a look at the graph in the first quadrant, right, and we'll use as our interval of integration from 1 to positive infinity. Okay. So 1 over x squared looks like this. And it approaches the x-axis. At 1, right, the function is defined right there. So at 1, I would... All right, well, we'll move 1 over a little bit. All right, so that's 1. And then we're looking at basically this right here. All right, so that's the area that I want to integrate over. So what I'm doing is, right, the antiderivative from 1 to infinity of 1 over x squared dx. Now, before I actually make any attempt to evaluate that, let's take a look at what happens if I make some finite sub-intervals here. All right, so if I stop this somewhere finite, and let's just call that t, right, then what I have is a finite interval, a finite area under the curve. And that finite area under the curve I can use the fundamental theorem of calculus for. When I do that, what I get is the area as a function of t. So that is going to be from 1 to t, 1 over x squared dx. All right, now we're making some assumptions here. Obviously, the way I drew it, t is greater than 1. All right, so I'm just going to make a little comment here that t is greater than 1. Greater than, not greater than, or equal to, so we have an actual area that we're looking at in the correct direction. And this I can evaluate, right? 1 over x squared is an elementary function, so it has an antiderivative. And that antiderivative is negative 1 over x. And we're going to evaluate that then from 1 to t. And when I do that, well, when I put in t, I get negative 1 over t minus a negative 1 over 1. So if I simplify this, clean it up, and turn it around, I get 1 minus 1 over t. All right, now I want to keep moving t along the x-axis further to the right. We have a way from Calc 1 to do that, right? If I'm moving t to the right, I'm letting t get larger and larger, and letting a value get larger and larger, arbitrarily large, is making it go to infinity. So now I can take the limit as t goes to infinity of a of t, which is going to be the limit as t goes to infinity of 1 minus 1 over t. And we know from, even just from Calc 1, that as t goes to infinity, 1 over t goes to 0. So this limit is equal to 1. So what that means is this develops a way for us to deal with infinite boundaries. Right? So what we have is the antiderivative from 1 to infinity of 1 over x squared dx, right, becomes the limit as t goes to infinity of the antiderivative from 1 to t of 1 over x squared dx. All right, and we saw from just above that that is equal to 1. So we have a function that has an infinite bound, right, or is unbounded, I guess is another way to say that. All right, a function that's unbounded, yet the area under the curve for that function is finite. And this actually is something that comes up a lot. So we're going to use this example as our guide as we define the integral of f. Not necessarily a positive function. This happened to be a positive function over an infinite integral. All right, as using it this way, using the limit. Now keep in mind, when we have a positive function, we can interpret that antiderivative as the area under the curve. Otherwise, it's just the antiderivative. Okay, so let's put together our definition here. All right, so we want to define improper integrals. All right, so first of all, the definite integral has to, the antiderivative has to exist. All right, so our first step here is if the antiderivative from a to t of f of t, of f of x, of f of x dx exists for t greater than or equal to a and t finite, right? So I can stop anywhere along the x-axis, take the antiderivative, and it exists, then the antiderivative from a to infinity of f of x dx is equal to the limit as t goes to infinity of the antiderivative from a to t of f of x dx. Now, we're allowed to make that equality provided the finite antiderivative exists for every value of t greater than a. Every time you stop, you can actually calculate the antiderivative. Now, that doesn't necessarily mean that the limit's going to exist. All right, so this is provided the limit exists. And we'll see some examples in a little while where it works and where it doesn't. All right, so it has to exist, and by exist I mean that it's a finite number. All right, now, if the limit is on the other side, okay, so the second possibility here for this is that we have the antiderivative from t to b of f of x dx exists for t less than b. Okay, t less than or equal to b. And again, t is finite. Then the antiderivative from negative infinity to b of f of x dx is going to equal the limit as t goes to infinity, t to b f of x dx. All right, so same idea as the one above. Right? I can move to the left on the x-axis and stop at any finite value and evaluate the antiderivative and get a finite value. Then I can make this equality. That doesn't necessarily guarantee that the limit exists. All right? So this is provided the limit exists. All right, now, if the discontinuity is between the two values, between a and b, that's our third case here. All right, so if both the antiderivative from a to infinity of f of x dx and oh, I'm sorry, wait, this is not the discontinuity. This is just our ability to split up. Okay. Right, that's the type 2. I'm only doing the endpoints this time. And where was I? The antiderivative from negative infinity to a of f of x dx exist, then we can add them together. Right? Then the antiderivative from negative infinity to infinity, that's an infinity, f of x dx can be written as the sum of those two. Plus so we can have, I probably should have written that the other way around, not a big deal. So we can have either the left-hand bound or the right-hand bound be infinite, or we can have both the left and right be infinite. But in order to evaluate that last case, you have to have the left, you have to be able to split the integral at a point, the function at a point, and both the left-hand side and the right-hand side have to exist. All right, so that means splitting the problem up into two separate problems. Okay, so let's look at, all right, so we saw up here one where we were able to actually find a finite antiderivative. Let's take a look at another one similar to that, and that is the antiderivative from 1 to infinity of 1 over x dx. Let's see what happens with that. All right, so if I follow my definition, what I'm going to do is say the limit as t goes to infinity of the antiderivative from 1 to t of 1 over x dx. All right, so that's my first step. Now I'm going to take the antiderivative of 1 over x, and the antiderivative of 1 over x is the natural log of the absolute value of x, and then that's going to get evaluated from 1 to t. So we have ln of the absolute value of t. Whoop, forgot my limit. Don't forget your limit. We have the limit as t goes to infinity of, okay, so now ln of the absolute value of t minus ln of 1. ln of 1 is 0, so this whole thing becomes the limit as t goes to infinity of ln of the absolute value of t, and that diverges. That goes to infinity. All right, so in this case, the antiderivative, right? The antiderivative doesn't exist. All right, since the limit, actually, I don't want to write it that way. Hang on. All right, so I'm just going to conclude from here. So the antiderivative from 1 to infinity of 1 over x dx does not exist. What we say, rather than saying it doesn't exist, is we say it, since the limit doesn't exist, the antiderivative diverges. Exist. Okay. All right, so we say it diverges. It's not finite. Okay, not finite. So there's an interesting comparison going on here, right? So if I have two functions, I have y equals 1 over x squared, and I have y equals 1 over x. This one, all right, let's put 1 in here. So here's 1. Here's 1. This one has a finite area. Right, this area, so I let that go out, is finite. This one has an infinite area. right? This one, this area in here is infinite. Now, you can interpret that geometrically, and you'll notice that both functions approach the x-axis. They both approach 0. But 1 over x squared approaches 0 a lot faster than 1 over x does. 1 over x does not approach 0 fast enough for that area to be finite. And that's pretty much the difference between the two. All right, let's take a look at another example. All right, how about this? Let's do the antiderivative from negative infinity to 0 of x e to the x dx. All right, so we use the second part now of the definition because our infinite bound is on the bottom. So this is going to become the limit as t goes to infinity, negative infinity, of the antiderivative from t to 0 of x e to the x dx. All right, now we have to integrate x e to the x, and that's going to be an integration by parts. So we take u equal to x, so du is dx, and we take dv equal to e to the x dx, so v is e to the x. And what we get is uv, which is x e to the x, minus the antiderivative of v du, so that's e to the x dx. So this is going to be the limit as t goes to negative infinity of x e to the x minus e to the x evaluated from t to 0. And so we get here, let's see, the limit as t goes to negative infinity. All right, so 0 is going to give me 0 e to the 0, so that's 0. And e to the 0 is 1, so that's going to give me minus 1 minus t e to the t minus e to the t. Okay. All right, so I need to now evaluate the limit. All right, let me just rewrite that without the parentheses, and I'll put the 1 at the end. All right, so minus t e to the t plus e to the t minus 1. Okay, so this half, and I dropped my limit again, didn't I? Try to be careful not to do that. Okay. So what I was about to say was this half here under the little squiggly bracket there is no problem. All right, because as t goes to negative infinity, e to the t goes to 0, which means that second half is going to negative 1. Okay. What I have to check is the remainder of this. All right, and the remainder of this turns out, all right, so I'm going to come over here and do some scratch. The limit as t goes to negative infinity of negative t e to the t is a L'Hopital's form, because this goes to infinity times 0. All right, that's a L'Hopital's form. So the way we deal with that particular L'Hopital's form is to take one of the factors and invert it and put it in the denominator. So the easiest one to do that with is going to be e to the t. So I'm going to take this and make it the limit as t goes to negative infinity of, let's see. Well, I guess I don't need the negative in there, because I really just need to worry about t e to the t. So let me take that out. I'll put the negative back in at the end. So that's going to be t over e to the negative t. All right, and now this goes to infinity over infinity. All right, so now this is infinity on the top and infinity on the bottom, which is still technically a L'Hopital's form, but it's one I can deal with, right? We deal with that by taking the derivative on the top and the derivative on the bottom. So t goes to negative infinity. The derivative of t is 1. The derivative of e to the negative t is negative e to the negative t. All right, which, as I simplify this, is the limit as t goes to negative infinity of negative e to the t. Right? And as e to the t goes to negative infinity, as t goes to negative infinity, e to the t goes to 0. That was a long way around to say this goes to 0. All right, so that first term goes to 0. All right, so let's take this around the scratch and down here. So we have right now the limit as t goes to 0 to negative infinity of negative t e to the t plus e to the t minus 1. All right, so we now know that the first term goes to 0. The second term goes to 0. The third term is a constant. So this whole thing is equal to negative 1. All right, so what we get out of this, is the final antiderivative from negative infinity to 0 of x e to the x dx is equal to negative 1. Right, and that is the final answer there. All right, so this is pulling together a lot of stuff. It's pulling together all of our techniques of integration along with L'Hopital's form from Calc 1. All right. All right, let's take a look at another one. All right, let's do one where both endpoints are infinite. All right, so let's do this. The antiderivative, negative infinity to infinity of 1 over 1 plus x squared dx. All right, now we can look at the graph of that. All right, if you look at the graph of that, and I think I forgot to put that in my grapher, so give me just a second. Oop. Because it's 1 over 1 plus x squared. Okay, so if we take a look at the graph right here, all right, you can see, I'll move it over and maybe zoom out a little bit. All right, you can see what the function looks like, and it's a good idea with these, especially when you have the ones that are, where both endpoints are infinite, take a look at it and see where you might want to split it. Now, you can split it anywhere, but looking at the graph, 0 seems to be a good place to split it, right? Because, first of all, the function's even, so its left-hand side and its right-hand side are the same, at least at finite intervals. It's true for an infinite interval too, but we're going to do both of them just to be certain. All right, so 0 looks like a good place to split it. So if I come back to the board here, and I make the decision to split this at 0, I'm going to go from negative infinity to 0, 1 over 1 plus x squared dx, plus 0 to infinity, 1 over 1 plus x squared dx. And so that's going to be that's going to be the choice I make to split that up. And again, just graph it, take a look at it, and see what looks good from the graph. All right, now I have to evaluate each of these. All right, so let's do this. I'll take the positive one first. All right, so that's going to be the limit as t goes to infinity. The antiderivative from 0 to t, 1 over 1 plus x squared dx. All right, now the antiderivative of 1 over 1 plus x squared dx is arctangent, or tangent inverse. All right, so this is going to be the limit as t goes to infinity of tan inverse of t. Tan inverse of x evaluated from 0 to t. There we go. That's what I wanted. All right, so then this is going to be, I think I can fit this in here. If I do, okay, so the inverse tangent of 0 is 0. So this is going to be the limit as t goes to infinity of tan inverse of t, which you can look at the graph, or you can go on your calculator, but it'll give you a decimal. Use the unit circle, however it is you want to do it. This is pi over 2. All right, so now we should expect, if this is an even function, right? This is an even function, so we should expect the other side to be the same. All right, so we're just going to verify that. All right, so the second side is negative infinity to 0, 1 over 1 plus x squared dx. All right, so that's going to be the limit as t goes to 0, as t goes to negative infinity, t to 0, 1 over 1 plus x squared dx. All right, same fundamental antiderivative. So this is going to be the limit as t goes to infinity of tan inverse, I just realized I wrote tangent, of tan inverse of x evaluated from t to 0. All right, so this is going to be the limit. Okay, so let me actually write this one out, because this one has a sign. All right, so when I plug in 0, I get 0 minus. When I plug in t, I get tan inverse of t. Tan inverse of t. I don't have quite enough room there, so let's come back here. All right, so as t approaches negative infinity, the inverse tangent approaches negative pi over 2. So we end up with 0 minus a minus pi over 2, which is going to be pi over 2. All right, so now we know that the area is the same on both sides, and even though the bounds are infinite, this is an even function, so it's behaving the way we expected it to behave. All right, anyway. All right, so what we're looking for is negative infinity to infinity. All right, so the first one was pi over 2. The second one was pi over 2. So this whole thing is equal to pi. All right. Okay. Now the other thing is, since again, we can tell from the graph, right? If I switch back to the graph for a minute here. If I switch back to the graph here for a minute, you can tell from the graph that this is positive, right? The function itself is above the x-axis, and that means that we can interpret this antiderivative as the area under the curve. So the area under this curve is pi. Okay. All right. Let's see. All right, so we saw, or I showed you before, a little bit earlier, the difference between 1 over x and 1 over x squared, that one converged and the other didn't. 1 over x squared converged to a value, it was finite, and 1 over x did not converge, it diverged. So let's take a look in general. All right, let's make a general, let's develop a rule here for functions that look like that. All right, so what values of p will this converge? Okay, so first of all, we can assume that p is not 1, right? All right, we've already shown, right? We've already shown that the antiderivative from 1 to infinity of 1 over x dx diverges. All right, so we're going to assume p is not 1. So we can assume p is not 1. So that means it's either greater than 1 or less than 1. All right, now, because this is an elementary function and it does have an antiderivative, I can evaluate the infinite bounded integral without knowing what p is, right? I just need to know that p is not 1 to know, well, I just know that if p is 1, it's going to diverge, but that doesn't matter, right? So let's take a look at what I get when we actually work this out. Right? So if the top, I need a limit. All right, this is going to be the limit as t goes to infinity. The antiderivative from 1 to t, 1 over x to the p dx. All right, so 1 over x to the p, that would be x to the minus p, right? So that's going to be, all right, you know what? Let me write that down. No point in confusing people. All right, so this is x to the minus p dx. So this is going to be the limit as t goes to infinity. All right, so x to the minus p, we add 1 and divide. So that is going to be x to the p, negative p plus 1 over negative p plus 1. And then we're going to evaluate that from 1 to t. Okay. All right. So let's do that. So what do I get when I do that? I get t to the minus p plus 1 over minus p plus 1 minus 1 over minus p plus 1. Okay. So I'm going to change that to be 1 minus p in a minute because I don't like that minus sign hanging out in front. So I have a common factor there that I can pull out. All right, I can pull out 1 over 1 minus p. And then what I'm left with is, I'll do it in 2 steps, t to the minus p plus 1 minus 1. Right? And t to the minus p plus 1, I can drop that into the denominator if I negate the exponent. So we're going to have 1 over 1 minus p. And then in here, that's going to be 1 over t to the p minus 1 minus 1. Okay. I think that's enough. So what we need to do is we need to see what happens to this when we take the limit as t goes to infinity, which I literally dropped at every single one of these steps. All right, I'm going to, if you've never seen it before, there's a shorthand that I'm going to have to squeeze in here for the limit. All right, I want t limit as t goes to infinity. Okay, t limit as t goes to infinity. T limit as t goes to infinity. That's a perfectly acceptable shorthand for the limit as t goes to infinity if you get tired of writing it. Or you forget to put it in and need to squeeze it into a small space. Anyway, so now I need to see what happens to that limit. All right, if p is not equal to 1, and we can see now why we don't want p equal to 1, even though we already know that diverges, that's going to diverge because 1 over 1 minus p. All right, so if p is greater than 1, so we have 2 options left. If p is greater than 1, all right, then what happens to this limit? Well, let's take a look at if p is greater than 1. Right? If p is greater than 1, then this is going to be negative 1. P is greater than 1. Oh, here's what I'm looking for. This is going to be 0 minus 1. Okay. And that's going to leave me with minus this term here. So, p is greater than 1, then this is going to be negative 1 over 1 minus p, or 1 over p minus 1. All right, so it's going to converge, and it's going to converge to 1 over p minus 1. If p is less than 1, all right, let's think about that for a second. All right, if p is less than 1, then this whole exponent here is going to be negative. All right, and if that whole exponent is going to be negative, then what we're looking at is t to the negative quantity p minus 1. All right, so let me come over here and do some scratch again. All right, so I'm taking the limit, it goes to infinity, 1 over 1 minus p. This becomes t to the 1 minus p minus 1, like that. And the problem that we have then is that if p is less than 1, this exponent is going to be positive, right? So if p is less than 1, then 1 minus p is greater than 1. Okay. And if 1 minus p is greater than 1, this limit is going to diverge. So if one part of the limit, one part of your limit, the t to the 1 minus p, goes to infinity, the whole thing is going to infinity. All right, so this diverges. All right, so this is sometimes referred to as the p-test. Okay. So, whoop, didn't mean to do that. Okay, so the p-test for improper integrals what it says is the antiderivative from 1 to infinity of 1 over x to the p dx converges if p is greater than 1 and diverges if p is less than or equal to 1. All right, so that's a quick way to do just a little visual comparison of these kind of integrals. All right, I'm going to stop here, and I'm going to continue with this topic in the next video.